Greetings everyone. I'm Venani Onkuru, and this is a review of a paper under topic a deep generative modeling architecture for designing lattice-constrained perovskite materials. As the introduction, the paper explores a deep generative modeling approach for material discoveries, and it focuses on designing lattice-constrained perovskite material with high symmetry. Variational autoencoders and generative adversarial network struggle to preserve lattice structure in generated materials. The authors propose the lattice-constrained materials generative model to solve this issue. The LCMGM combines SSVAE and AGNAN to enforce structural constraints, and it improves physical validity of generated materials with advances deep learning applications in material sciences. The multi-layer perception and activation functions like MLP are used in SSVAE and AGNAN for features extraction, applied for property prediction and classification. Neural network consists of neurons, weight biases, activation functions. Rectified linear unit helps mitigate vanishing gradient issues. Sigmoid is used in classification for probability output. Unless is learning in high dimension features space of perovskites facilitates nonlinear transformations in deep networks. The neural networks architecture are such as the input layers, processes, mesh grids, perovskite representations, and the hidden layers use convolutionals and full connected layers for features extraction. And the SSVAE output are such as regression, which predicts formation in energy, classification, which it identifies crystal system. A GAN output generates latent vectors preserving structural constraints, balances exploration and exploitation, and it improves representation, leading to for perovskite structures, ensures higher stability and better chemical diversity. The learning paradigms and adversarial strategy. The model applies semi-supervised learning, integrating supervised and unsupervised methods. And SSVAE learns unsupervised latent space and refines it with labeled data. And a GAN uses adversarial learning to generate new materials. Discriminator evaluates generated samples for chemical and structural validity. Generator produces novel perovskite structure with realistic constraints. It improves model generation and stability. Advances machine learning in material discovery. are the error correction and optimization, backpropagation and gradient descent minimize the construction loss, Bayesian optimization, which refines lattice parameters for stability. Also, there is Kullback Leibler, which which diverse which the divergence loss in SSVAE regularize latent space, preventing overfitting. A GAN auxiliary predictor reduces risk of mode collapse and ensure the generated structure are chemically varied and thermodynamically stable. Optimizes deep learning workflows for materials properties prediction, improve accuracy or in structure generation. Yeah, this is the mesh description, which figures are here. Invertible mesh grid description for perovskite. There is A which is a structure atomic model for Ra2VRE06 perovskite with green, with flag green, V purple, red gray, and O red. B XRD pattern simulated X-ray diffraction indicating crystallinity. Mesh grid projection, 3D mapping, material property and labels into structured grid. And all these are explained by this figure. And the lattice-constrained material generative model, which is LCMGM, is also like this. And for the phase one SSVA, it encodes perovskite structure into a structural latent space using RGB representations. And there is coupled MLPS, which extracts material property embedding E1, C1 from the latent space. And also we have phase 2, which is a NAGAN. Also we have phase 3, which is a BO and DFT. And also Bayesian optimization, which is BO. Conclusion, future work. LCMGM integrates deep learning and a physical-based constraint for material discovery. Key strength is to improve training stability, chemical diversity, and structural precision. The future work includes expanding crystal system and integrating reinforcement learning, optimizing computational efficiency which will enhance complex materials discovery. And this model represents a major advancement in computational material science. And this opens new possibilities for AI driven material design. These are references. Thank you so much.